This is about an idea that I had for some time, because if you want to build a wireless speaker, what you typically find is something, well, using a Raspberry Pi W or something like that. Raspberry Pi 0 and run a Linux on it and put a Snapcast client on it, and then everything works with not too much work. But I thought, well, you don't really need that much hardware for that. So I decided, well, I would like to try a wireless speaker with less hardware. So going really to the small systems, and I can probably not build it on a system that only has 16 kilobytes of memory, because the problem is the sound decoding. That takes some RAM, but fortunately we have here with the Raspberry Pi Pico or the RP2040, we have actually nearly 300 kilobytes of RAM, and that is plentiful. So I really don't need that much. So I'm Detlef Vollmann. I live in Switzerland. Originally I'm German, and yeah, I do some contracting. My day work is currently on a server doing C++, and so in my spare time I work on these small systems. I'm also in the C++ committee and try to put some things through that are useful for small systems. So I will start with my idea, and then before that, everything I will show you on code you can find in my GitLab repo. It has a strange name because I actually presented some parts of this at EMBO++ 4 weeks ago. So that is a repo. And well, as I already said, the original idea was to build a wireless speaker. And if you want to do it yourself, you have to look for a protocol, and the usual protocol for that is Snapcast. And I don't really like that protocol very much because it uses TCP instead of UDP, which I think would make much more sense. But on the other hand, you get the server for that and all that. So I use it right now. And the sound comes encoded. It can send Ogg Vorbis and some other thing, PCM, not decoded. And you can send Opus. And when I looked at all the decoders, I thought, well, for small systems, the Opus decoder would probably make more sense. And, but as that is a lot of work to do, the sound decoding, I decided to go for a dual-core system. So my original setup was this. I have the first core for all the I/O and the second core for the sound decoding. And the original version is the hardware that I didn't bring, and that actually is an Espressif ESP32. And unfortunately, that has a core, the extensor, which is not very well documented. And it turned out pretty hard to do a native task switch on that one. So what I did then was to base everything on FreeRTOS, but I didn't like that idea very much. So then I looked at the Pico, and the Pico W actually also has a Wi-Fi modem. which is connected via SPI, and because they didn't want to spend too much GPIOs for that SPI, they have a special SPI and do that with their programmable I/O controller. And the I2S is the same, that they don't have dedicated hardware for that, but just use a PIO, which is fine. Unfortunately, the Wi-Fi didn't work out because that modem there, the documentation for that is, yeah, it's nearly non-existent, and what I found is quite probably wrong on documentation, and so Wi-Fi currently doesn't work, and I still wanted to show something, so I currently just use the UART to stream all the data. And so I modified the Snap server a little bit. It was only about 10 lines or so that I had to change, so that works. And so why do I use the RP2040? Well, it's easy available. It's an ARM core, which is very well documented. You can find essentially everything about that in public documentation. And for the RP2040, the documentation is not too bad. You sometimes notice that those people don't have very much experience in writing documentation for these microcontrollers because it simply lacks some information. It's not because they want to hide it, they just forgot to mention it, but they have a pretty good SDK, and you can use that SDK as documentation. I can't use that SDK directly. I will come back to that later. And it's pretty nice hardware. So here is the main part of my implementation. So you have seen those queues. The first queue is for the incoming Opus frames. That is actually pretty big. For the UART, it's not so important, but if it goes to Wi-Fi with TCP, I can get quite some latency, and so I want a bigger buffer. For the outgoing part, so after decoding the PCM, I only need a small buffer because there is not too much latency there, which is actually good because the PCM frames, of course, are much bigger than the Opus frames. And right now I spent about, I think, 20K for the Opus buffer, and yeah, only 4 frames. However, those frames are pretty big for the PCM buffer. So these are my queues. And of course, I have to set up all the hardware and things like that. And then I actually have 2 execution contexts I use. One is on the first core, which is more or less standard multi-threading preemptive scheduler, where I can throw any task on it. And the problem is purely historical. Currently, I need that on the first core to get everything else work. I don't actually need to do any work there, so I just put 2 dummy tasks on it. One to blink my flash, my LED, to flash my LED, and the other thing is just to put out some statistics, how many frames I got and sent out. Yeah, just for fun. The real work is going on in interrupt service routines, which are not scheduled through that execution context. And then I have so-called single context, so I can only run 1 task in it. But that runs directly on the hardware. I also have some loop context somewhere else that can run in a thread or something like that. But this runs directly on hardware, and that is important if you go for interrupts, events, and things like that. So here I start my decode function on the second core? Well, actually, I only set it up. This here actually starts everything. Well, let's see how it works. So switch off, switch on, LED blinks. You see some output. So the decoder started, which is fine. And here I have already set up my snap server. And here I actually sent some sound to it. And sorry, it sounds horrible, but that is just my setup here. It's neither the software nor the hardware itself. So you can see something. It's not nice to listen to that, so I will stop it again. But essentially it works. So you have seen quite a lot of things here. So the rest of the talk is, what are all those things? So these things are C++ OS. So what is C++ OS? Well, the idea is, well, C++ actually has already a standard interface for quite a lot of system things. And there are coming more. And, but that is just an interface, and the standard library is not an operating system. So I decided to provide an operating system that implements more or less a full C++ standard with a standard interface. So that is the idea of C++ OS. And it's a hobby project, so it's far from complete. It's very buggy. It has a lot of debugging code still in there and so on. But it's a nice thing to try out all those things. And why should you do that? Well, of course, all the usual reasons for using a standard apply, but the real reason is well, I have never written an operating system before, so I thought it's time to do that. And it's fun. It's actually not that much work. And so I did it. And so the goal is actually to implement the full C++ interface on very small systems where you have more or less kilobytes and not megabytes, gigabytes, or whatever. And you need some specific things for small systems, like my single context. That is something you probably don't need on a Linux, but you need that for these small things. And I have an implementation for native ARM. The original one was for Cortex M3, M4, but not for floating point. Then I did one for the 8-bit AVR. So it works on that one as well, with only 12 kilobytes of RAM or something like that. However, not this specific thing, but C++ OS. And then I did the port for the Cortex M0. And as I said before, for the ESP32, the native implementation wasn't that easy, so I did an implementation based on FreeRTOS, but I will probably not work on that anymore. And if you look, what does it mean to provide the standard library? Well, fortunately, I don't have to write the standard library myself. There are a lot of standard libraries around. Well, for the small things, there are not so many. Especially if you look for AVR, probably libstdc++ is the only one that is more or less complete. And however, it provides much more than just the freestanding part. So if you look, for example, and then the libstdc++ is pretty nicely layered. So it provides you with everything for chrono. You just have to provide the now function. Everything else works out of the box. A similar thing is for mutex. All the log things are there. You only have to provide the mutex itself. But all the things around that are already there. And libstdc++ can be built for essentially all the platforms that are supported by GCC, which are quite a lot. And well, sometimes if you actually do that, you find some problems, but Jonathan Wakely was actually pretty fast to fix any bugs that I reported. And so those gaps that needs to be filled, that is the idea of C++ OS. So what does C++ actually provide? Well, it provides a lot of things. For concurrency, for example, it provides thread and async. I didn't implement that because, well, very often on these small systems, you don't create threads on the fly. You set it up at the beginning, and for that, the execution that we have now for probably C++ 26 is a much better model. But I have implemented mutex and condition variable. I haven't implemented yet ledge barrier, semaphore, and atomic weight. However, my mutex can be more or less used as a semaphore, just not as a counting semaphore, but you can lock in one thread and unlock in another thread. And the memory model is a compiler thing, so that works anyway. And atomics are pretty complete, and that is not libstdc++, that is actually the compiler, but it's essentially the same. You only have to provide some basic functions, and then everything works out of the box. Well, and about time, I already talked about chrono. For sleep, well, that, of course, is not chrono. That is actually in the thread header, and that makes a lot of sense because it's actually specified as blocking the current thread, which means more or less main or what you create by thread, but not something else. And I will come back to that. But I implemented that. So here you have it. There are no timers in the standard library so far. And I think one of the reasons is we don't have any event mechanism anyway right now. We have some ideas about for coroutines and sender receivers, but right now we don't have anything, so we don't have timers. I actually implemented a timer because you need that. And yeah, I already talked about events. And events is something that you just have in embedded systems. Well, you have them in non-embedded systems as well. As soon as you are asynchronous, you get an event, more or less. Everything where you block, well, we heard this morning you should never block, but sometimes you have to block, for example, to wait for user input or whatever. You get notified by an event. In an embedded system, that is often an interrupt, it may be something else. We don't have an event system yet in C++. We have at least something that cares about the interrupt service routines, because you can see interrupt service routine as a signal handler, and we care about that in the memory model. And we had the networking TS that had a full event system, but that will not get standardized. And for actually some good reasons and some not so good reasons. We have coroutines, but that is a mechanism how you can handle events, but not how you actually equate or block on events. So that part is missing. So yeah, we have to wait for that, but you may see something at the end. And then there's also file system. I currently don't care about file system. But of course, there's a lot more in the standard libraries, which is really useful for small system. Even that stuff that is not in freestanding, it's very useful. Things like string or vector. I don't provide malloc, so you don't get new out of the box. However, with PMR and the memory resource stuff, you can just use vector and string and vector of strings using the PMR. You just have to provide your allocator. So I have here my static allocator, and that is just based on a monotonic memory resource. So I don't really have to write much for that. And with that, I can specify a vector of int and initialize that with some values. I can have a vector of strings. And then I can use pushback for int, or I can use pushback for strings. It just works. And actually, it does work on the Avion, on the 8-bit system, with 12 kilobytes of RAM. So much about general C++ support. Well, the interesting part is, well, we have 2 cores here. And actually, we have here 2 cores. That I have 2 Picos. One is for the JTAG, and one is the real thing. And so to start things, you need something where they can run on, and these are executors or execution contexts. And we have a proposal that originally started out as a proposal to care for heterogeneous computing resources. Well, they mainly thought about GPUs and things like that. Well, I think about the second core in my Pico, but that is fine. However, all these things were removed from P2300, and so what is left over right now is just an event handling model. Not an event model, but an event handling model. And it's currently aimed for C++ 26. And, but at least it mentions execution context, and it provides the execute function that you have seen in the code, if you look carefully. And so execution contexts are actually the thing where you run on. So execution contexts provide execution agents. And the execution agent is called a scheduler in the P2300. And so an execution agent could be a thread. The execution context is what gives you the thread. So it could be a thread pool, for example. Interrupt service routines actually are execution agents as well. They are some execution resource. And of course, if you have another core or you have a GPU, you have other executions, things that can execute things, so you can have execution context for them. However, the execution contexts are just mentioned. There's absolutely no API specified for them, and absolutely no requirements. I hope we can change that, but right now, that is what we have. However, what is specified is that execution contexts have to provide schedulers. It's not specified how they provide them, but they have to provide schedulers. And schedulers actually must work together with the global function schedule, and then you can start something. but then you can only start something using the sender-receiver model. Well, I will show something like that at the end, but there's also another function, which is the execute function, that you can also run on a scheduler. And with that, you can run tasks on a scheduler. And yeah, as I already said, in P2300, everything that was in there about the execution context was more or less thrown out. So they don't propose any concrete execution context, but there are other proposals. So we currently have a proposal for a thread pool. And in C++ OS for the small system, I actually have actually four execution contexts that I provide. One is the classic pre-emptive multitasking execution context. That is the exec context. And then I have the single context where you can only execute one task on it. But you can use coroutines or whatever inside of that. I also have a loop executor, which the single context runs on hardware. The loop executor that can run inside of a task that runs inside of the execution context, for example. And then I have an interrupt context. I didn't implement that for the RP2040 yet, but I have that for AVR. So let's look at some more code. So again, here I have, well, because that execution context is actually a pretty big thing, but I want to control the initialization, so I have some space, some global space somewhere, and I just use the placement new to create the actual object inside of that one, and that is my exec context. And then I get a scheduler. I get an ID of that scheduler that gets stored, so I can use it for debugging or things like that. And this is a stack size. As I said before, this interface is not standardized. So how you get your scheduler, it's completely up to the execution context. So I decided to do it this way, to put everything into template arguments so I don't have to store them. And these 440 are bytes, not kilobytes or something like that, that are bytes. And so if you ever think about coroutines, you definitely don't want to go, the coroutine frames go onto this stack. They have to go somewhere else. So we have the first task that just blinks my LED. I have a second task that just prints some numbers, and those numbers are actually computed by 3 busy tasks. Well, that is something you typically don't have in small embedded systems, something that just consumes all your computing power. But for testing the scheduler, that is actually a pretty useful thing. So I just have 3 busy tasks that have all the same priority. And I actually could have a third template argument here for the priority. I just use a default priority for all of them. And, but I have 3 busy tasks. They just count different counters. And those counters are actually atomic. So here I have my counters. And well, I have counter pointers, and these are the counters that are actually atomic 32-bit values. And for example, for the AVR, it's very important that they are atomic because even a load and a store are not atomic. You cannot atomically load 32 bits if you are on an 8-bit machine. Doesn't work. And now my print task is here. So I actually have the sleep. And to be honest, I don't use stat format here. I'm just not used to it yet. And I didn't implement the stream buffers. So I also cannot use IO stream. So I use my own very simple debugging UART with a simple write function where I give a buffer and the length of a buffer. But at least I can use the toCars function from the standard library. So I do this, and so what I do is I just print the current time and all the counters from the busy task. The busy task is very simple. It just gets some initial parameter that tells it which number it has. So it will take that counter and will just increment the counter. Yeah. The point is I have a local counter here, and I give a pointer to this counter to the global thing. So here I store the address to my local counter. So I don't need the global counters that I had in the other one. And then I just count. Nothing else. And the LED blinking, so it looks like more, it's actually much smaller. So I just sleep, and then I toggle my LED, which is just a very simple GPIO class with a toggle function. And that's it. So I've already built it, so just download it. So now you saw this blinking because it was downloading it. And here you already see, well, it started somehow, but it doesn't blink. For some reason, the Pico RP2040 is, it looks like pretty hard to reset. So resetting via JTAG often doesn't work. So I just power cycle. And now the LED blinks. And here after 5 seconds or something like that, it should, after 10 seconds, it starts to print something. So, fine. Any questions so far? So, let's look again at the hardware. Because that hardware is actually a very special hardware because it is based on an ARM Cortex M0 Plus core, which is definitely not designed for multi-core. Because it's only ARM v6, not ARMv7. And only the ARMv7 has the instruction for load locked store conditional. So all the things you need to do synchronization between multiple cores. But they decided to put 2 of these cores into the MCU. And I actually have read in a Raspberry Pi forum by an engineer from Raspberry Pi. Well, they didn't want to spend the money on the hardware, so the software people have to fix up for it. And that's actually the case. So what they did is they put in some special hardware for the synchronization. So you get a register that you can read on which CPU, on which of the core you are running, the CPU ID, 0 or 1. And then you get 32 hardware spin locks. And I think a read will lock it and write will unlock it. And if you read a 1, then the lock was successful. And if you read a 0, then the lock was not successful. And you have a FIFO with about 16 entries or something like that in both directions between those 2 cores. And that's it. You have to live with that. So it is some kind, well, SMP sometimes is called shared memory processing. And it definitely is shared memory processing because those 2 cores share exactly the same RAM. It is not really symmetrical multiprocessing because, well, there's no cache coherence. Well, why is this cache coherence in quotes? Because, well, we don't have a cache here. So it's not really about cache coherence, but it's about a mechanism where you can detect whether those 2 cores modify the same memory location. And you need something like that, and you don't have that. So in that sense, it's not SMP. So the original port, well, that was easy because I already had a port for the M0, so it just worked more or less out of the box. I couldn't use the Pico SDK because they do stuff that C++ OS does as well. So they have some mutex things and things like that, and they also do some memory management and things like that. So it just doesn't fit. And so I decided to work without that, which is okay. For most things, it didn't work out for the Wi-Fi, but otherwise, it more or less works pretty well. So I have support for single core and the exit context for the mutex, condition variable, atomic. Atomic is, I think by now it's nearly complete for the standard atomics. I have never tested the atomic flag. I just use an atomic pool for that, but that's okay. And it might actually work because the compiler might internally use something like the atomic pool anyway or something like that. So that was the original thing. However, well, for communicating that something happened, well, you need something that is often called event. And we actually, well, the point is atomics, when they are log-free, work everywhere. However, for everything else, you need a mechanism to tell somebody that something happened. So For things like mutex and condition variable, they are not specified if you are not on a thread. So if you are inside of an interrupt service routine, you don't want to use those things anyway because they are blocking. However, yeah, how do you tell that something happened? Sometimes it works. So notify out of an interrupt service routine actually may work. It may not work. In my case, it works. But it's not really a good thing. So I will come to queues in a moment on the next slide or the one after that. Assume you have a queue and you have a coroutine waiting on it and you have a normal thread pushing into it. How do you communicate between those two? There's currently no mechanism for that. Well, we actually had quite some time ago, you see that if you look at the number, we had a proposal, might have been 2016 or something like that, by Torvald Riegel, who actually had a paper how to communicate and synchronize between threads and coroutines. And he proposed an event. He had a rough sketch of an event class with some function, block and notify more or less, and it never went anywhere. So it was briefly discussed, and we said, well, it looks interesting, but Torvald Riegel decided not to come to the meetings anymore, and so this was dropped. I always liked the idea. So actually, I used this event as the underlying mechanism beneath my mutex and condition variable that I implemented anyway. However, originally, I only had them for my only execution context that I had, which was the exec context. And for that, I just hard-coded everything, and that worked fine. However, it really only works between tasks that run on my exec context, and in my case, it also runs in an interrupt service routine. It doesn't really work if you are on the other core in a single context, because there's no notification going to the other core. So you need a mechanism for that. And so if you communicate between different execution contexts, you can actually have a so-called M2N problem. Because for each pair of execution contexts, you need to implement this stuff. So far, I got around to implement with only one execution context. So when I notify, I have to give the notify function the execution context in which the notify runs as a template argument, and I have different implementation for the sending thing. And if I'm blocking, I have to implement that on different execution contexts differently as well, because if I'm blocking on a multitasking executor, I just switch to the other task. If I block on a single task executor, I just call wait for interrupt. So it goes to sleep. And so I actually took those events and used them, and now I have them as templates. I have currently a very weird interface, so that will change because I have the notify. I currently have only the notify one, but I could also do the notify all because it only depends on the sending context, not on the receiving. So even if there are a lot of different receivers, for example, on a mutex, a lot of different execution agents could currently wait on a mutex. That is fine because I'm only depend on the sending context. And I have this on the event itself, but the block I have on the execution context. Which makes sense logically, but it doesn't make sense from the user perspective. So I probably will put both of them into the event. But of course, in both cases, it needs special support from the executor, and that needs to check. And for the notify thing, you really need some common knowledge. So you need to establish some common interface that you can use. So in my case, it's pretty easy. Okay, if it goes to the other core, I just have to send a message to the FIFO. If I would be on a Linux system, I would probably have to put everything through a file descriptor because at some time I want to use select or poll or something on that. And that on Linux only works on file descriptors, so I have to go through file descriptors. But I have to need this common mechanism that works more or less for all, and I need to know what I have to do for that. And based on those events, I can implement queues. And queues are a very important mechanism, for example, getting data out from an interrupt service routine into the application task, or in my case, communicating between the receiver. If it's a network, it's the same. I just push the received data packets from the network into the queue, then the decoder pulls them from the queue, decodes them, pushes them into the next queue, and then the I2S task pushes that to the hardware. And so that is a very, very useful thing, not only on embedded systems. And of course, for interrupt service routines, they have to be log-free. And yeah, if you look at anything, at all the examples from sender-receiver, they look like pipelines. And if you hear pipelines, well, at least I immediately think, okay, between those different stages of a pipeline, there are queues. Sender-receiver doesn't work that way. So as it's currently specified, I believe it's not possible to do it that way. So I actually have some kind of implementation for the sender-receiver, but I ignored that part of the specification. So I actually allow to put queues in between them so that that could actually work. And yeah, of course, if you have queues and want to use them as an active thing inside of your pipeline, of your sender-receiver pipeline, then both the push and the pop functions need to return with senders. But that's a different thing. So C++ OS, well, I have the classic queue, and then that was essentially just a mechanism to test my mutex and my condition variable. So I actually use standard implementation using mutex and using condition variable. And that works only on the execution context where my mutex and condition variables work. It also works from interrupt service routine if I use the try versions only. So if I only use the non-blocking functions, but that is fine. But that doesn't work with my second core and my single context on that second core. So I also have event-based queues. And these now are special because, especially for the blocking part, but also partly for the notifying part, I need the execution context. So what I actually have for these event-based queues is I have a queue body which holds the data, and then I have front ends for that body, for the push and for the pop. And those front ends are templated on the execution context. So in theory, I could actually have multiple pullers. I have to admit I didn't implement that. So right now I assume that on both ends there's always only one. But it shouldn't be too hard to implement. The other thing, Make Michael has a mechanism where you can even use ring buffers with multiple pushers or pullers, and so that should actually work. So let's see how it looks like. So this actually is not demo code, it's the raw code, so it has a lot of debugging in there. But I think that's actually not a bad idea. So here I specify the size of my queue. So it doesn't allocate memory. So when you set up the queue, it will use the memory that you specify, actually in my case, as a template argument. So you do absolutely no dynamic memory allocation. So here I have my queue body. I just push ints in there, and I have my queue size. So Q1 is my queue body. And in this example, I only use a single context, a single core, so I only use my exec context. So both ends, the push and the pull, both use this my exec t, which is the exec context. So push Q1 is the push end on Q1, pull Q1 is the pull end on the on Q1. And then the same with the second queue. And here's all my debugging stuff. And here is my first task. So I just start to push numbers into the queue, and then I print the number. Lint stands for logint, and it prints the line number and the actual integer. And then I sleep for half a second, and then I push the next one. And after that, I just close it, and after that, I just go into an endless loop because I never should end a task that I set up. The second task, that actually starts with sleeping for 10 seconds. And after that, it just pulls or pops on the first queue and pushes it into the second queue. And if the first queue was closed, it will also close the second queue. And in the third task, again, I start right away. This time I only use try pop. And I check the status. If it's closed, I can stop. If it's empty, I just sleep for 100 milliseconds and then I try again. And yeah, again I have my LED task and my print task, just to see that everything is alive. And here I just set up all these tasks. So what I have is I have the first task who pushes numbers into the first queue, but they are not popped for 10 seconds. So after 16 elements, that is the size of my queue, it has to stop, it has to block until the second task eventually starts and starts to pull the values, and then it will just go on and push 100 numbers through both of the queues. So for this I need the second UART. And here I change to qtest preempt bin. And again, I just upload it. So here you can see that the first task is busy pushing values into the queue, but after 16 it has to stop and wait. And then the second task starts, and now it goes on until it reaches the 100. Questions? Okay. So let's go multi-core. I don't provide classic SMP, so a task can never go from one core to the other. And that is just a design decision. There's no reason in the hardware why it couldn't do that, but because all the RAM is shared, so all the stacks are shared, and so I could actually migrate them, but I decided not to do that. And in most cases on those small embedded systems, you don't want that anyway. You really want to decide what runs on which core. So tasks can never migrate. So what I have is that on the first core right now, I have the exec context, and on the second core, I have the single context. And I could actually run the single context on the first core as well. Right now, it wouldn't work well with the interrupt service routine, so I don't do that. But yeah, there are only minor things that I have to fix there, because I still need some global list of all the tasks. And currently, my exec context keeps that list. I just have to put that somewhere else. And after that, everything should work. And on the single context, whenever I block, I right now, I actually do the wait for interrupt, so the processor goes to low power sleep until an interrupt comes in. Originally it didn't work, but probably it was just my mistake, because now it works pretty well. And of course, to start the second core, you have to go through some very special steps that are very well defined in the documentation with the code in the SDK, so I more or less just duplicated that code, and that is fine. Right now, I use a single interrupt vector for both cores. I will change that in the future, because that will make many things simpler if I have really my interrupt context on this hardware as well. Atomic load, atomic store, 32-bit, works out of the box. That is atomic in this architecture. However, any read, modify, write is not atomic. So all these I have to protect with a spin lock. Right now, I use one single spin lock for all atomics. So if you have a lot of atomics, they will all contend on this single spin lock. Well, I have 32 spin locks. Well, some of them should probably be reserved for some application usage or whatever, but probably I could use something like 16 or so for this and just use the address as the key, just a part of the address as a key into that. So that's not too bad. However, if you stay on the same core, you don't need to use an atomic. Use volatile for that. Everybody tells you don't use volatile for any cross-thread communication. Well, as long as you are sure you stay on the same core, you can still do that. And it's much cheaper. So do this. And as I said before, I have a FIFO and I can send my events through the FIFO, which creates an interrupt on the other side. So my wait for interrupts actually wakes up and it can handle the event. So that's all. So I have changed a few things. One of the more interesting things is sleep. My sleep doesn't work in single context because my sleep is actually based on the scheduler. The scheduler looks, well, somewhere I have to store the time when I wake up. And I actually do that in the task block, because one task can only sleep once. So I can have that value in the task block. So the scheduler looks into the task block and check whether the wake up time is reached or not, and then it will put their tasks to ready. On a single task, I don't have anything like that. So here I need my timer. And actually, I think that is also the reason why this is one of the very, very few places where the standard actually says thread, not execution agent or something like that. It actually says thread. And it is also deliberate that it is a namespace, this thread. So you can only run it if you are on some kind of thread. Single context doesn't run on a thread, so you cannot use that. So we use a timer for that. And I have 4 timers, 4 simple timers that I can use on this hardware. And so the 0 here is just the number of the timer. And then I didn't implement yet the chrono stuff for my wait function, so you have to give microseconds. And but that is fine. So what I do here is I just wait for 10 million microseconds. So I wait for 10 seconds. So this is one thing I changed. The other thing I changed is, of course, now I have 2 different execution contexts. And I have to adjust my front ends of the queue for that. So the pull for the first queue and the push for the second queue are now templated on my single context. And that's essentially it. So now I have 2 execution contexts, and I start nearly everything on context 0, and only this one, which is task 2, on the other core. And that's it. So again, let's download it. And now the second task puts out on the second UART. So you see that here. And yeah, now the 10 seconds are over, and you see all the numbers here. Well, and the wireless speaker, which is not wireless here, is exactly the same. So again, I have my queue bodies. And maybe let's start with the second core, which is a decode. So here I create my front ends for my, again for my single context, for the decoder, so the pull on the first queue and the push on the second queue. And again, I need a timer here. This time I use timer 1. I probably use a timer 0 for my output stuff. And then I have to set up all the Opus decoder, and I just took the standard library. Well, you can download that from some place. It's open source, and I just put it into my repo and to just use those functions. And I have to initialize that decoder. And, well, I don't have a semaphore yet, and I cannot use my mutex for the single context. So the idea is that I don't start decoding on the very first frame that arrives, but because I want to fill my buffer first, for at least a little bit. So I decided to wait on the first frame, just throw it away, and then sleep for some time, and only then start. In the original version that was based on FreeRTOS, there I have a semaphore. I just use a semaphore, and so I counted on the incoming side and just released that semaphore, and it worked that way. And I will eventually do that here as well, but right now I use just a timer. And after that, I just have my endless loop. I wait on the queue. Well, by this time there should be something in there, but after well, maybe at some time I really have to wait for it. And yeah, then I use the decode function from Opus, and I push the result into the PCM queue. And that's it. All this is just debugging and information. So, and in my main, well, let's look. That is actually somewhere else, but because to compile that part, I actually currently need the Pico SDK for the PIO stuff. So I have put that into a static library. And so that is somewhere else, and I and here there's a setup that is not so interesting, but here's my interrupt for the DMA. And the interesting thing is this here. So I do a pull. Well, this is the consuming thing. So this is the I2S. So I pull a frame from the queue. If that doesn't succeed, I just send some output anyway. I just send some silence. And otherwise, I just get everything. I set up my DMA to send that frame to the I2S machinery. So here I have the pull PCM frame that is called from the interrupt service routine. And I have the same oops. How is it called? Ah, receiver. And this is for the UART. And again, I will wait on the UART, and if the DMA gives me some data from the UART, I use a function called push chunk. But those use the Pico SDK, so they cannot use anything from C++ OS, so I have to provide these functions somewhere else, and I provide them from my main. So here's the push function, and it creates the pushing end from for the first queue, and even if it runs in an interrupt service context, interrupt service routine, I don't have an interrupt context here, so I actually use my standard exec context, and that works fine. And so I always use the try version because I'm not allowed to block inside of an interrupt service routine. And the same for the pull PCM frame. Again, I create my end of it, and again I do a try pop, and if it doesn't succeed, I just return a false, so that the interrupt service routine knows it has to fill in some silence. And again, that's more or less it. That is a lot of setup I need to do. These are my two execution contexts. And that is what I have already shown you. And that starts everything. So I need to stop this one. Because now I need that UART for my snap server. I probably need to stop this and start it again. That is a snap server. So now the board is ready. It blinks, and so you can hear the horrible sound again. Okay. Mission accomplished. Things that I'm currently working on, well, the first thing is coroutines. So if I have coroutines, I don't need to do a scheduling. And scheduling, well, on this hardware, it isn't really that bad, but on the AVR with 16 megahertz, well, it's, I think it's about 600 or 700 cycles to do a full context switch, including the scheduling, to find out which task is scheduled. So that is quite a lot. And so you can avoid that if you use coroutines. However, for doing useful things with coroutines, you need an event loop that actually looks, okay, this coroutine is waiting on this, and this event now happened, so I can resume that coroutine. And I have actually started on that one. And so again, I will use my queues, but I need to, well, I need to push into the queue from the interrupt service routine, which cannot be a coroutine. And I need to pull from it, from the coroutine. So yeah, I need exactly the event loop. Just having a queue that does both push and pop inside of coroutines, that is simple. You just do a ping pong, more or less. And that is easy. For that, you don't need your event loop. But if you have some external events then that are not caused by another coroutine, then you really need your event loop. And I have all the pieces I have somewhere, I just haven't put them together yet. However, what I have put together is how it would look like, but it's slide code. It doesn't even compile yet. So, so essentially what I have is, well, instead of task 1, 2, and 3, I have, it's the same example, but now I use better names for it. I have my own promise type here, which is trivial, and it's for a void. And, well, whenever I want to sleep, I cannot sleep inside of a coroutine. I have to use a timer for that. I have only 4 timers for this program. I need 6 timers, so I have to solve this problem as well. But that's a different problem. However, what I do is I just have to provide a co-push on my queue and have to correlate that. And then for pull, exactly the same. Oh, yeah, it's slide code. Because this, of course, needs to be await. Co-await this status equals co-await this thing. So here is a wait missing. And here again. But that's it. And with that in place, well, I cannot start the coroutine directly from my single context. I need a normal function for that. Like main cannot be a coroutine, or the starting function of a thread cannot be a coroutine. And so I have my all function here, and here I more or less start all those coroutines. What is missing here, again, slide code, something like this. So now I need to start the event loop, and that looks that as soon as something happens, that correct coroutine is resumed. And with that, I don't need all this. I only have a single context. And then I run everything on that. So sender receiver, well, this is something I did only for the AVR, not for the ARM yet. And so, yeah, again, you often just use a queue, and you have your interrupt context, and you have your application. And so if you want to use sender receiver, that could be a way to do that. Again, not according to the current spec, but hopefully we can change that. So here I have my interrupt context. Here I have my loop executor that just runs in the current thread, but I still need an executor for that. So I run the scheduler on my interrupt context, because that is where I start. Then I run the timer start. Then I use a queue with a size of 4, which is my buffer, but I transfer to a different execution context, which is the application. And there I do my print, and I run this forever. So that is, and that is actually an example that runs on the AVR. So, some final words. Why should you use it? You shouldn't. Very simple. Because it's a proof of concept. It's a nice toy to try out things. It's definitely not production code. And yeah, all the code can be found on GitLab. Here are some references. My slides will probably show up on my website sometime, hopefully soon. And that's it. 3 minutes for questions.